Hello, my name is Alfred Bresnik. I'd like to show you the EmonaTIMS Telecommunications Instructional Modelling System. TIMS is laboratory teaching equipment that, if you look on page 3 of the TIMS brochure, you'll see is intended for telecommunications systems courses in introductory and advanced labs. In the telecommunications lab, the students learn the math and the theory associated with coding and modulation in telecommunications. Once the students have this fundamental knowledge, they then move to specialised labs where they learn about the implementation of these theories and these technologies in optics, RF circuits and so on. Within these TIMS labs, TIMS is able to implement a very wide range of modulation and coding schemes. This card illustrates the telecommunications transmission model, where a message may be encoded, modulated, passed through a channel, demodulated and decoded. On this card you can see the wide range of telecommunications theories and concepts that TIMS can implement. The challenge in telecommunications teaching is how to show students so many different forms of modulation and coding with a single piece of equipment. TIMS addresses this challenge in the following way. If we turn to page 5 of the brochure, we'll see the TIMS example. The TIMS example here illustrates the unique method that TIMS uses to implement such a wide variety of experiments. First of all, we start off with the telecommunications theory or the math. In telecommunications textbooks, these theories, this math, is represented as block diagrams. What TIMS does is it goes the next step. TIMS actually implements, actually brings to life these block diagrams as real electronic functional blocks. Page 2 shows textbook-like waveforms which are actually generated on the TIMS system and captured on an oscilloscope. In this example, we see there are multipliers and there are adders. In the TIMS implementation, we can see there's a multiplier and there is a multiplier. There's an adder and there is an adder. And the links between the blocks in the block diagram are actually the interconnections between these TIMS modules. Students build the experiment, the encoding or the modulation scheme, following the block diagram in a systematic and engineering manner. They need to take measurements at each point to confirm the operation against theory. So they measure and vary amplitude, phase, frequency or synchronization. The end result is then compared back to the theory, and the students need to take account of the differences between the math and the actual electronic implementation. Each block in the block diagram is actually a TIMS hardware plug-in module. If we look over at page 4, we'll see an example of the TIMS modules. On the top are the blocks of the block diagrams, and below are the TIMS modules. So we have a sine generator, we have a sine generator module. An adder block, we have an adder module. A multiplier and a multiplier block. Using this approach of these fundamental building blocks, TIMS is able to implement this very wide range of experiments ranging from adding and multiplying signals right through to multi-level 4, 8, 16 PSK and QAM systems, trellis code modulation, as well as DSP and other implementations. All TIMS modules follow very strict conventions in order to make the modules easier to use for students. Looking at this module, the inputs are always on the left, the outputs are always on the right. Notice that they are never calibrated. This is because the student needs to actually measure the frequency or the phase or the amplitude that's required. This is about setting levels, not knobs. In this way, students are prevented from patching together experiments using a cookbook approach. They need to measure in an engineering manner each parameter as they build the modulation or the encoding scheme. The TIMS system includes 3 units. First of all, the system unit, 13 basic plug-in modules, and a range of over 50 advanced modules. System unit, 13 basic plug-in modules, and a range of over 50 advanced modules. Each of these modules are fundamental building blocks. No one module is an experiment on its own. If we look at the system unit, it includes an upper rack which has provision for 12 plug-in modules. In the lower rack we have the fixed modules which are used most often in each experiment. The basic plug-in modules are fundamental building blocks such as adders, multipliers, filters, phase shifters, sequence generators, and so on. The advanced modules include a wider range of building blocks to implement more advanced digital and analog modulation and coding schemes. If we look at page 9 of the TIMS brochure, we'll see a description of the TIMS 301 standard system. It includes the system unit, it includes 13 basic plug-in modules, it includes user manuals, and 2 forms of experiment documentation. First of all, the TIMS student texts, which are detailed step-by-step experiments, and 80 lab sheet experiments which give the instructor a quick start on how to implement any of the TIMS schemes. The student text and the lab sheet experiments are increasing all the time. Here we can see the listing of the fixed and the basic modules included in the TIMS 301 standard system, and below we can see the range of experiments that the 301 system can implement. If we turn the following 2 pages, we can see in detail the basic modules, their front panels and block diagrams. On page 12 we can see a concise listing of the TIMS advanced modules, and the following pages all provide detailed descriptions and front panel diagrams for the 50 or so advanced modules. The last 2 pages of the TIMS brochure list the modules that are required in each of the lab sheet and each of the student text experiments. The EmonaTIMS telecommunications instructional modelling system is an open-ended and expandable system. As new modulation and coding schemes are developed, they can be implemented on TIMS either with existing modules or with new modules, or you can develop your own modules within your school. In fact, TIMS open architecture guarantees that you will be able to implement any telecommunications scheme, encoding or modulation scheme as it is developed.